right.
Do you know what day it is?
Wednesday, January 9th. All right.
Good job.
Hello and welcome to the Weekly Space Hangout for Wednesday, January 9th, 2019. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about the first views from the far side of the moon. More fast radio bursts found. Let's see. And we weren't going to talk about what's happening with New Horizons, right? We feel like we've got enough.
Oh, no, we should.
We should
Totally
want
should.
some more New Horizons stuff. All right.
To say.
And a quick update on what's happening with Mr. Stevens' attempt to catch a fairing from SpaceX. Joining me this week, you heard them already in the background. We've got Dr. Morgan Randberg. Morgan.
Hey, Fraser. Hey, Kim.
And, well, spoiler alert, Dr. Kimberly Cartier is here as well.
Well, hello. I suppose you already know that I'm here. It's podcast day, and a happy one.
Right on. Paul is out shamelessly self-promoting his book for some kind of book launch thing. So we're holding the fort, but we do have an interview. And we'll be getting to that at the end of the show. All right. So let's begin. Morgan, let's talk about the moon.
Yes. The moon is cool, and we're there again. And this is the royal we, because we're talking, of course, about the Chinese Space Agency, which pulled off a real impressive mission, or at least the start of a real impressive mission this last week with the landing of Chang'e 4 on the far side of the moon. This is the first time we have we being humankind, has ever landed something on the far side of the moon. And China didn't just land one thing. They landed a rover and a lander. So this is going to be kind of a two-part mission.
I'm going to show people this story from Kimberly Cartier. Yeah.
The pictures I've been getting back have been great. So we have the Chang'e 4 lander and the U-2 rover. You might remember U-2, the rover that landed on the near side of the moon back in 2013. And this is an upgraded version of that same design. But sort of the twist that makes this even more complicated is that the far side of the moon never faces the Earth. That's kind of obvious. And so communicating with the far side of the moon is basically impossible. You can't send a radio signal from Earth to the far side of the moon, no matter what you want to do. And so the first thing China had to do was, about summer last year, is send a communication satellite out beyond the moon. And it's orbiting in this sort of circular orbit around the Earth-Moon Lagrange point, L2. So this is a stable point in space where that spacecraft can kind of just hang out. And the orbit that it's on means that sometimes it's in sight of the rover and lander, and sometimes it's in sight of Earth. And so it can act as a relay back and forth. And this is a sort of a mission archetype that basically has never been done before. You think about the rovers that NASA has sent to Mars, going all the way back to Pathfinder, but Spirit and Opportunity and Curiosity and upcoming Mars 2020, all of those missions had the opportunity and the capability to directly communicate between Mars and Earth. Now, that wasn't how they usually do it. Usually they relay through a Mars orbiting satellite. But if worst comes to worst, they can always send commands and get commands back directly from Earth. That's not the case here. If this communication satellite stops working, there will be 0% communication between those objects. And so this is sort of China, a new space power, pioneering a new way to run a mission. And sort of throwing in on top of that, hey, we can't communicate directly. That's a feature, not a bug. And they're actually going to conduct radio science experiments on the far side of the moon that could not be conducted anywhere on Earth or anywhere in Earth orbit or low Earth orbit, because the terrestrial radio signals from your FM radio and your internet and everything just pollutes outer space. But on the far side of the moon, it's radio silent, and they can listen in for these faint signals coming from outer space.
Yeah, it's really, really cool, the sort of the geometry and the tricks that they're using to get this done. And the place that they're exploring near the South Pole in this crater is actually a really fascinating place, because the South Pole Atkins Basin, we think was a site of a very large impact sometime in the moon's history, and the
Could be the
entire
biggest in
area,
the solar system.
yeah, and the entire area could be flooded with what used to be inside the moon's mantle. This is material that we can't actually get to and see nowadays, but this is a place where it might just be strewn about the surface. So we could get a up close and personal look at what it's actually like inside the moon.
And there are permanently shadowed craters at the south pole of the moon. And although they've detected the water ice from space with some of the orbiters, this is the first time that they might be able to actually see some of these right there from the ground. So a whole bunch of firsts.
Yeah, the geologic sort of mystery of the moon's surface has been a puzzle for planetary scientists, basically all the way back to like 1960, when the first missions that were then just flybys flew past the moon and gave us our first ever pictures of the far side, because the far side of the moon looks nothing like the near side. Yeah. It has way more craters. It has very, very few lava flows. It has a composition that appears to be markedly different than what we see on the near side. And there's really no clear reason why that should be. People have put forward various hypotheses, but there's no obvious reason that the far side of the moon and the near side should basically be night and day different. And yet all of the samples that we have from the surface of the moon have come from the near side. All the Apollo missions, the Soviet missions that returned samples, even the Chinese lander that will hopefully land in the next couple of months and return another sample. All of that's been from the near side. These are our first direct measurements of the composition of that far side regolith, which hopefully will provide some chemical hints about what's different that maybe we can use as a data point to spin into this larger story of why the moon seems to have like two totally different faces.
What are some clues that they could find that would tell them that to give some idea of why the far side of the moon looks so different?
So you'd want to see like compositionally what the surface is made of. Because if you look at the near side, the dark regions are made of different kinds of rock than the lighter areas. And that's because the dark areas formed as sort of lava flows bursting out of ancient volcanoes on the moon's surface. We don't see nearly that kind of material, at least from orbit, on the far side. So I think one simple question would be, does the lighter material that we see on the far side of the moon match the composition of the lighter material we see on the near side? So that would be like sort of the basic structure of the moon. And then from there, things have been perturbed over time. Or are we looking at a totally different or even slightly different composition, which would suggest that all the way back to when the Earth and the moon were forming, something was different. And that's kind of one of the hypotheses that is advanced, is because the near side is closer to the Earth, it's experiencing tidal forces much stronger than the far side. We think of the moon raising tides on the Earth, but you have every action has an equal and opposite reaction, Newton's law. Those same tides are being raised on the moon. And if the near side of the moon was experiencing more tidal stretching, that could have driven volcanism, provided heat to drive volcanism that created all the volcanoes that we see on the near side. And the far side didn't experience that. And so in essence, the far side could actually be the older, more unperturbed side of the moon, at least chemically speaking.
And did I read right that this lander or rover was carrying some seeds or plant material with it?
Yeah, they're going to carry out some experiments to see what it's like to germinate plants on lunar gravity. I think it's probably not a surprise that it'll work. Like, we've grown plants in microgravity and it works. And we've grown plants in Earth gravity and it works. And so this is kind of an in-between. And if I were the scientist, I'd be interested in seeing sort of at the moon's gravity, basically 1/6 of the Earth's, is it look more like plants that are grown under full gravity or more like plants that are grown under microgravity? It's like one of the challenges we have with microgravity plants is they often bloom just fine or grow or whatever just fine for one generation. And then if the second generation basically just dies, or won't germinate. And is that a radiation problem? In which case the moon is just as bad as low Earth orbit, or is that a gravity problem? In which case the moon might be better than low Earth orbit. But if we ever plan to grow plants on the moon, we got to answer these questions.
It's not just plants, though. They also sent animals. They sent silkworm eggs to the surface of the moon.
Yeah.
To
Now, is this the first time that we're bringing plants and animals to the surface of another solar system object?
I think
Yeah.
so.
intentionally.
The Mars 2020 rover is going to carry a similar experiment to Mars. But I don't. Maybe
but that's in 2020.
Oh, the Apollo astronauts did bring seeds to the moon's surface, because around the world there are these moon trees that were planted with seeds that went to the surface of the moon.
Gotcha.
But they didn't water them and try to grow them. They were just in a bag.
Just brought them to the moon and back.
Right.
Exactly.
That's really cool, though.
Yeah. Question from David Dunn. I think it's a great question, which is, what's the best way to keep up with the latest data from this mission? We're so used to NASA and ESA and all of these news agencies, but my Chinese is a little rusty. So how have you guys been getting original information about this?
I've been getting actually most of my information from the Planetary Society, who has a corresponding reporter with close ties to a Chinese news agency. And that's how I've been getting a lot of my information, and then spawning off from there.
I read Kimberly's stories.
I did write about this.
Truthfully, China doesn't publish much in the way of English language content around their space activities, and they don't release pictures very widely. Only a small handful of pictures have trickled out from the Chang'e 3 mission that carried the original U2 rover back in 2013. We got a couple of panoramas, some surface shots, but nothing like the sort of boundless trove of data that comes back from a NASA mission.
For people who are wondering, the person I'm referring to, his name is Andrew Jones, and you can find him on Twitter. And that's sort of where I've been sourcing a lot of my stuff.
I think they read a lot of their stuff off of Weibo, which is the Chinese version of Twitter.
Yeah, I mean, it's a whole other gigantic news agency network structure that we're just not as tapped into as local Chinese journalists are. It's definitely, it feels for sure like one of my blind sides with, and it's something that I've been planning to try and improve with Universe Today, is us getting better access to what's happening with China. Like they launched the most rockets. They're planning to send humans to the moon. They have landed on the far side of the moon. Same thing with India. There's a lot of really interesting things that are coming out of India, and the problem is that they just don't disseminate their information over on English news sources in the same way that NASA. We're also comfortable with all this structure of the way the news moves around, and so it's about having to learn a whole new way to gather my news. But I plan to do it. So if anyone's cracked it, please let me know.
Yes, me too.
Yeah, exactly.
That'd be great.
Yeah, I know. It's a whole other
sort
of infrastructure that we just have no access to right now. So it would be interesting. I keep planning to do an episode about China, sort of the future of Chinese space exploration, and then I have no idea what to say. So, all right. Well, let's move on. Kimberly.
Yeah.
Since Morgan stole your story.
No, it's okay. I wrote a story about this one too. It was a busy week last week for space science and missions. So last week we talked a little bit about the New Horizons flyby of MU-69 on New Year's Day. And when we reported on it last week, we had, I think, 1 or 2 images at most about of this object to try and draw whatever conclusions we possibly could. And we were able to say a few things, like it's a contact binary made of 2 roughly spherical-ish type things smushed together with a very shiny, bright neck. It's reddish, and it's pretty small. That's probably about all we could say last week at the time we were recording this. And then the following day, there was another press conference with even more information and more data that the New Horizons team had probably been sleeplessly poring over for the entire week since the flyby to get results. It's honestly quite impressive how much they were able to tell us within a week. And so we did learn some new things about MU69 since the flyby. Things that include information about its elevation changes on its surface, some rough idea. There are hills and valleys and ridges, and they estimate that there's elevation changes up to 1 kilometer in height, which for this object, which is only 31 kilometers long and 20 kilometers wide approximately, having a 1 kilometer change in elevation is pretty big. So roughly spheroidal, quote unquote, it's pretty hilly. And with a couple of images, they started to put together a sort of a stereographic image, a 3D image of what it's actually like on this surface. It's very low resolution, given that they have like 3 images to work with.
Yeah.
But it's a start. And they can get an idea of its rotation. And they have learned that it rotates actually pretty slowly, much slower than they thought it would, at a 15-hour period. And it's slow because for 2 objects to collide together, you'd expect some sort of faster rotation. But they think perhaps that after the 2 lobes, they're calling them, came into contact together, they may have gotten impacted by something else that slowed down the rotation. Which brings up another mystery of where the heck those other objects are. Where are the moons? Because this thing doesn't seem to have any moons. So from a collision without any moons or debris around it is kind of weird.
It's interesting sort of how they put out their information after that. As you said, they came up with another press conference moments after we all got busy.
Literally in the middle of writing this article about it from the first press conference, then the other press conference started, and I was like, wait, no, I gotta redo everything.
Yeah, because they provided all this additional scientific information.
Yeah.
But at the same time, the pictures, we still don't have that big close-up, really high-resolution picture yet. They've
those
got
are very big images. They'll take a while to get here.
Right. We'll see those
so
in a
there's
few
some
more
of the
months.
So these are sort of the lower resolution images they were taking on approach, still, half an hour out from the object. These aren't the close-up views of the surface. We don't have information about whether there's craters or not. Probably yes, but we don't actually know that yet. Or any finer detail about the surface, sort of the elevations of these ridges or the divots and deeper indents that you see, the exact dimensions of the neck, any sort of compositional information. We're still waiting on all those data. But one of the things they did have is a map of the reflectivity of the surface to get an idea more quantitatively where the bright spots are and where the darker spots are. And we can say now that bright necklace, as I'm calling it a necklace, it's a bright spot around, it's a shiny spot around the neck. It actually is the brightest spot on this object. It reflects a whole 13% of sunlight, which is twice as much as any other spot.
You mentioned a couple of other things as well. Atmosphere, ice.
Yeah. Atmospheres and ice. So they don't think that it has an atmosphere. There's no reason to suspect it would have an atmosphere. It's pretty tiny. Its gravity's pretty low. Any sort of lighter atmospheric material would probably just wisp away. They're still going to look. And right after the flyby, they did swing New Horizons around to get a backlit view of MU69, which is the same thing they did for Pluto, to get that gorgeous image of like the 7 layers of haze above Pluto that we all stared at and just like in awe. They swung around to grab one of those images of MU69. That image hasn't come in yet, but they don't suspect an atmosphere's there. And as far as ices go, one of the initial theories of why this object was red was they said Pluto's reddish, Charon's reddish. That's because there are some exotic ices on the surface that have been irradiated and cause it to look red. Maybe that happened on MU69 as well. That's probably not the case because objects that small don't tend to have those kinds of ices on the surface. They tend to more have water ice or ammonia ice, which wouldn't cause that sort of redness. They're still going to look. They took spectroscopic data to try and figure that out. We don't have those data yet, so that's still sort of up in the air.
That red color isn't particularly uncommon for Kuiper Belt objects. And I think this kind of gets at the value of flying by MU69. Like, we flew by the biggest Kuiper Belt object, Pluto, but most Kuiper Belt objects are probably a lot more like MU69 than they are like Pluto. And so if we can understand why MU69 is red, we might understand why a huge range of Kuiper Belt objects are red, many of which we haven't yet discovered. But as we sort of improve our statistics, we're going to find fewer and fewer 300 or 400 kilometer objects and many more 50 kilometer or smaller objects. And this will be the key to unlocking sort of some of those basic observational properties of those guys.
And part of the reason why we didn't get as much data we didn't get all these new pictures, et cetera, was shortly after the flyby, New Horizons went out of contact, right behind the sun, I think.
Yeah, so the angle, again, angles of communication, as viewed from Earth, New Horizons was behind the sun since, right after the flyby. It's actually going to be back in contact tomorrow. So
apparently it's already back in contact.
Oh, lovely.
Yeah.
Cool. Yay.
So
it's already back in contact. It hasn't died yet.
Let the data download continue. So that's part of the reason why we don't have as much information and as many photographs as we would hope to at this point, just because.
But it's good because now the New Horizons team got like a whole week of sleep after like a whole week of not sleeping to just get us any sort of information possible.
That's
hopefully
awesome.
We'll get some new stuff soon. I want to see more of the 3D images to get a actual picture of this thing. I want a full rotation. I want to see all sides of it. I want to get actual dimensions for each of the two halves and the neck.
Yeah,
that's what I'm looking for.
That's great. All right, so before we move on, I want to give a big thank you, as always, to our good friends at the Weekly Space Hangout crew. These are our producers, these are our friends, these are our fans, and together we make this show. And if you want to be a part of this amazing community, go to wshcrew.space. They are completely independent. We have no control over them, but they help figure out what the guests are going to be, help us figure out what kinds of stories.
They do have control over us.
Yeah, they have control over us. We don't have any control
Scary
over
amount
them.
of control.
Yeah. So definitely go to wshcrew.space and join them and be a part of the chat that's going on during the live show, especially now that Google Plus is wiping out its communities. And I still haven't figured out how. I have one of the larger communities on Google Plus, which I know is sort of meaningless, right? It's a bit of a paradox.
Congratulations.
I know.
The tallest molehill.
Exactly. I need to figure out what to do with the 1 million people that are in the space community on Google+. All right. Well, before we move on to a larger story, I just wanted to share just a great little video here, and hopefully you guys can see. I'll share this at you, my co-hosts, as well. Here, let's see. All right. So we're going to see... All right, here we go. Start again. So this is, of course, the SpaceX Mr. Steven, which is the ship that has been built with a huge net on top, designed to catch the fairings that come off of the rockets as they launch, the SpaceX rockets. And so this is an example of one of these fairings coming back after the launch, deploying its parachute, and then floating gracefully back to Earth. And at the same time, the ship, Mr. Steven, madly chases it across the ocean. And so far, Mr. Steven, even with its upgraded huge net, has not been able to catch one of these fairings yet. They've gotten very close. And this latest one shows just how agonizingly close they got.
Oh, so close.
Oh, man, look at that.
Yeah. Yeah, and there it is in the drink.
And there we go.
So, yeah, it's really too bad. But they'll get it. They'll nail it. And,
You need a better engine on that speedboat.
Yeah, exactly. Well, and so each one of these things that's dropping down is worth $5-6 million. And if they do 30 launches over the course of a year, it is a big pile of money that is floating back to Earth and is well worth catching.
The water.
Yeah, it's well worth catching it. And
do they have a plan for improving the chances? Sure, eventually they're going to catch one. But if their odds are 1 out of every 20, then that's not that great. With the rocket landing, we saw them incrementally improving, and it was clear that they were going to get it even if they hadn't gotten it yet.
Yeah.
Does it seem like they're incrementally improving here?
I mean, they just make a bigger. They put a bigger net on it, right?
Bigger net.
Yeah. So this net is dramatically larger than the last net, but clearly it is still at the very limits of what they're able to do, how they're able to chase this thing down. To have a parachute that can somehow steer itself.
Can you put a bigger or better parachute on it so you don't have to deploy it quite as high and you can calculate the trajectory more accurately?
And it
I don't know how this works.
Yeah, no, I know. I mean, when you think about that, you have to calculate the motion of the fairing with the parachute, with the wind speed, and also pilot the ship to be able to catch up to it. I think that they'll crack it. It could very well be that they figure out a way that the parachute always turns at a very slow, very predictable rate, so it's not getting farther away from where the boat is. Perhaps they will be able to eventually even be able to steer with the parachute, or just a bigger net.
This definitely isn't one of those imagine a spherical cow traveling at 10 meters per second in a vacuum type of situations. Spherical cows? No? Anyone?
I saw like a picture of the spherical cows. Who's you're gonna have to explain it now.
It's an intro physics joke. Don't mind me.
You started this. You're gonna have to finish this.
I did.
That's it? We're done?
That's it. It's the quintessential intro physics joke. Everything is completely oversimplified and in no way physical.
Right.
And in no way resembles any sort of real life situation you'd use it. The end. Physics.
Physics. All right. So now the other piece of news that I'm going to be talking about today is this is just a piece of local news, of course, which is that Canada did a thing.
Yay!
Yay! So
in space?
Here on Earth. So there is this mystery, and we've mentioned this in the past. This idea of fast radio bursts. These are these weird blasts that come in the radio spectrum. They appear once, and then they never see them again. And what is the cause of these is a gigantic mystery, and literally astronomers just throw up a collective murr. But Australians helped figure out that, in fact, these things are not coming from the solar system. And this was sort of over the last year. So they know they're coming from outside the solar system, potentially outside the galaxy. And in Canada, there is a really sweet half-pipe, also telescope called CHIME. It's actually located relatively near to me here in British Columbia. And so what CHIME does is it's actually designed to help sort of scan and help provide more information about the cosmic microwave background, about the expansion of the universe, search for dark energy, dark matter. But one of the things that it does is it's able to find these fast radio bursts. And so just today, they announced that they found another 13 examples of these fast radio bursts. But one of the things that's really useful is they found the second time they've ever seen a repeating burst. So this is where a burst occurred in the same place as before. What are they? Like I said, astronomers just sort of have, they shrug their collective shoulders.
We've got more idea now than we had a couple years ago because of that first repeating burst.
It's something potentially to do with neutron stars, with,
So what is it not? Do we have an idea of what it's not?
It's not a ray gun.
Do you want to hear the aliens proposal? No.
Well, it's not something like a supernova. Although, one of the ideas that I think maybe we're hitting on now is maybe there are two classes of fast radio bursts. There's whatever creates the repeating ones. And we think the first repeating one is probably like a neutron star that's either being ripped apart by a black hole or being caught in a supernova blast of another nearby star. And there might be a second category that we seemingly only happen once and never repeat. And those could be a broader range of things like some particular class of supernova, for example. So, but I think that what's interesting about this was just how easily this Canadian telescope found them. Like, the telescope's not really even supposed to be working yet. Or by the time they were making these detections, they were basically turning it on and off as they were testing various components. Every time they'd turn it on, they'd find a fast radio burst. And so it suggests that they must be out there a lot. And to basically turn it on a few times and accidentally catch a repeating one tells us that maybe these repeating bursts are not nearly as rare as we thought they were. And if that's true, then in the next few years, we'll have a bunch of them and we'll know what they are.
It's thought that there's about 5,000 of them going off every day, so they are very common. But the amount of energy that is clearly being emitted, one estimate is about 25 million times more energy than the sun releases, but it's only in a millisecond. So
these are definitely things that are outside our galaxy, because if they were in our galaxy, we'd basically like see them with our naked eyes. There are billions of, I mean, they're radio bursts, but they're billions of light years away, and we catch just a faint glimpse of them because that energy is spread out across the whole universe.
Well, they actually weren't certain that, because you could have gotten something, it was thought that they could be coming from satellites. They could be reflections of Earth-based transmissions that are coming off of satellites and things in space, or even potentially things that are in the atmosphere. And that's why I was mentioning this Australian radio telescope is very farsighted, so it's incapable of focusing on objects that are within the solar system. And so because they were discovering them with this Australian instrument, it told them that definitively they had to be coming from outside of the solar system.
And what is this Canadian telescope supposed to be looking for? Or what was it designed to look at?
Right, so it's a radio instrument that's designed to help sort of scan the large-scale structure of the universe in radio waves. So things like helping to tease out dark matter, dark energy, the expansion, of the universe after the Big Bang. I don't think that they had intended, I'm not certain, but I don't think they had intended to be searching for fast radio bursts when they started to design and build the telescope itself.
It wasn't clear, I think, that this telescope would be sensitive to them, because this telescope is sort of measuring a lower frequency radio waves than the Parkes radio telescope, which is the one in Australia that Fraser's mentioning. And it wasn't obvious whether fast radio bursts would have enough power in these lower frequency components to be detectable. But the answer to that seems to be categorically yes. And it's finding them more efficiently maybe than any other telescope.
Yeah.
Well, that's pretty cool.
Yeah. Well, it is one of those big, genuine mysteries that I think has slipped under the radar for a lot of people. Not necessarily dark matter, dark energy scale. This feels like one of those mysteries that we're going to get our hands on and figure out shortly, thanks to tools like this. But at this point, astronomers have no collective position on what is causing such a energetic event that only happens this one time.
Well, and there's
except for the repeating.
The first one was like 2007. It's the first time we detected one, and so we're just trying to get our head around them at this point.
And I think this will lead into the conversation that I'll be having with Lucianne Walkowicz in a second, but that there is this whole sphere of time-based astronomy, things the universe is doing when we're not looking, which we just don't watch the universe enough to see all of these kinds of events. And as new surveys come online, more time-based surveys like the Large Synoptic Survey Telescope, it's going to be a golden age. It's going to be a ton of new weird events that no one's ever seen before, that happen on an irregular basis, that suddenly have some, that is a new puzzle for astronomers to figure out. And like I said, I don't want to spoiler alert the interview, but we talk about one that was a completely unexpected situation, and a weird thing that stars can do, which when they saw this in the data, they had to figure out what was going on. So
you'll never guess what astronomers caught a star doing.
Number 4 will shock you.
All right. So, and we will shift into that interview in a moment. But before we do, I want to sort of give my co-hosts a chance to talk about what they're working on. Kimberly.
Oh gosh, what am I working on now? Now that New Horizons and the moon stuff is done, my brain is sort of empty right now. I'm working on some longer term projects that have to do with Apollo, and have to do with some like reviews of how we've advanced our deep space maneuvering since Apollo. Because between then and between now and approaching, MU-69 and approaching Rosetta, the technological differences are huge. And so I'm working on a project exploring that.
Morgan.
Bigger rockets. We talked a lot about exploring the moon today, but this is actually going to be a huge year for lunar exploration. And I have a video out at SciShow Space looking forward to the rest of 2019. We didn't even write about this because we knew it was happening so soon. But predicting in the rest of the year, there's these huge milestones of lunar exploration that are going to take place. And it just also happens to be the 50th anniversary of the Apollo landing. So it's going to be a great year for the moon. And I had a lot of fun sort of peeking ahead at what might be coming.
Well, and I have sent out to the patrons, but tomorrow I'll be dropping my new video all about Techno Signatures. And this was NASA's Techno Signature panel came together back in September and came up with recommendations on how we could be searching for evidence of aliens impacting their environments. And
You can say the M word. It's okay.
that's just one of the
I won't
the
unfriend
things.
you if you say it.
Megastructures. But no, there was, I mean, some of the more interesting ideas in there. Things like, for example, the Square Kilometer Array, which is this new monster radio telescope that's getting built, will have the ability to detect leaked radio transmissions from alien civilizations out very far into space, the kind of transmission leaks that we would have here on Earth, and that's 2030, so soon. And some of the other really interesting telescopes that are in the works. So there's some cool ideas on what we can do to expand our ideas of how to search for life out there. All right. Well, so I want to say a big thank you to, let me just shift here. There's the gallery view. There's all of us. So we're going to say goodbye, and then we're going to shift into the episode, the interview that we had. And like I said, it's a really good interview. So if if it's because it's not live, you don't care, you should totally watch it. It's really good. But I'll let my co-hosts head off to enjoy the rest of their evenings. Thanks everybody for watching.
Bye.
Bye.
See you guys. All right, let me go back to me. Let me bring up the interview. And let's get started. All right, here we go. All right, joining us this week, we've got Lucianne Walkowicz. Lucianne, welcome to the Weekly Space Hangout.
Thanks for having me. Great to be here.
I can't believe we've never interviewed you before. Like, we hung out down at Google like 5 years ago.
Yeah,
and,
kind of a while.
and have been sort of going in the same circles. But I'm so glad we could get you here on the Weekly Space Hangout. For people who don't know who you are, who are you? What do you do?
I'm Lucianne Walkowicz, and I'm an astronomer at the Adler Planetarium in Chicago. I work on a variety of different things. Do you want a little summary?
Yes, please.
Sure. I work on a variety of different topics. My background is all in studying exoplanets and how stars affect whether planets can be good or bad places to look for life, maybe for life to develop or even thrive. And more recently, I now work on applying something called machine learning to sift through vast piles of astronomical data. And most recently, I spent a year at the Library of Congress as their chair of astrobiology, doing research on the ethical and social implications of humans going to space.
I don't even know where to start. All right, so there's three things I would love to talk to you about. The ethics of humans going into space is fascinating. Sort of the current state of searching for biosignatures around other worlds, and sort of just the future of big data with telescopes like the Large Synoptic Survey Telescope. So I just reminded myself to talk about those three topics. Let's start on the ethics side here. Spending a year thinking about should humanity be in space, what conclusions did you come to? Should we be in space?
I think it's really hard to sum it all up. I don't think I can give you a simple answer to should we be in space. I think the question is really not so much a question of whether, but also a question of how. So one of the things that I've been thinking about this stuff for a couple of years now. I actually gave a TED talk back in 2015 about this idea of like Mars as a backup planet, that, you know, like the reason that we should go to Mars is to like back up humanity. And I find that to be a really problematic idea for a variety of different reasons. But thinking about it in this past year at the library, I think one of the things that has really come home for me, and something that, you know, I am constantly reminded of working in a planetarium and speaking with the wide variety of people that I do, is that people have very different ideas about what humans should do in space, if they should go there at all. You know, my favorite thing to do here actually is talk to our Adler teens, because they have some really great ideas about, you know, like whether they would go personally, and then also who should go. I think, you know, my favorite answer to that question was one of our teens who said that we should send the US Congress to space, and if they come back, then they can have their jobs.
Right.
So, you know, when you ask a wide swath of the population, you know, like, should we go and what should we do there? You get a lot of different answers, you know, and I think there's a lot of room for nuance. And the thing that I've really enjoyed thinking about at the planetarium is how, at the planetarium and at the Library of Congress, is how that landscape is shifting and maybe changing by private companies, you know, whether it's Blue Origin or SpaceX or whoever, really being interested in having greater autonomy when they go to space.
So I guess there's sort of two issues there, right? One is like just like the ethics of sending human beings to a horrible place where they're probably going to starve, die, and have trouble breathing, and, you know, have cancer later in life. And then there is sort of what are all of the legal, political issues with sending super megacorps to Mars to strip mine the surface and claim ownership in a place that in theory is there for all humanity. So is it even ethical for us to send people? I mean, I guess we can't stop them necessarily, but I mean, we don't know what the low gravity is going to do to human beings. We don't know what some of the other issues there. I mean, do you even think we can live in a place like Mars?
Well, you know, one of the actual like physical side of it, like the effects of like long-term space travel on the human body, is really like its own field. One of the things that I find very interesting about it is looking at how medical ethicists have approached those questions. You know, as with any kind of undertaking, like there's always, you know, forefront in the issue is like informed consent, right? People can decide to do any variety of things, you know, like leaving space totally out of it for a moment. You know, like somebody can go try to hike across Antarctica, and they can make that choice even though it's very dangerous for them. One of the things that is complicated is what you mentioned, in that there's actually no way for a long-term space flight mission, you know, let's say to Mars or something like that, to meet the health standards that NASA has for its astronauts. And so there's, first of all, the issue that you can't make a completely informed decision because you just don't have the information to do so. You can also give consent for something and then withdraw that consent. And when you're on Earth, you can withdraw the consent and you have a chance of going home.
Yeah, I've had enough. I want to come home.
Yeah, but you know, when you're in space, it's not like you could even if you could like turn everything totally around and head back immediately, you still might have a long duration of time in which you are there still in a space that you no longer consent to. And so one of the very interesting things that I found is that the policy for any kind of like mission to Mars, for example, is that each and every single one of those missions has to make the decision of whether the mission's goals are worth violating the astronaut health standards, because there's no way to meet them at all. Like you can't. So I thought that was that decision to to choose to actively violate those health standards is really interesting. Now, if we're talking about like private tourism and like space, like maybe private space companies sending their own astronaut corps, then it gets even more complicated, right? Because you have now a wider variety in the kinds of bodies that might be in space. There is still like a really relatively small fraction of the global population has ever been to space, and they tend to be drawn from a fairly homogenous, like mostly European population,
Right.
put through like a ringer of tests. And so they all represent a certain kind of body, and when you make that more broad, you don't know what some of those other effects might be. And so one of the really interesting things from this past year is like talking to scholars like Ashley Shue at Virginia Tech, who studies disability and technology, and how our ideas about like who is the ideal astronaut have been formed around this idea of like a certain kind of body being perfect for space. So, she discusses how, like, for example, deaf men who had lost their hearing via getting an infection that made them also immune to motion sickness, they were studied as a way of taking not deaf men and putting them in space instead of somebody being like, well, what if we just send the men that are already immune to motion sickness to space?
Or give astronauts crippling ear infections.
Right.
The ethics are complicated. I understand this.
Yeah.
But the and then of course there are all of the the sort of the legal and ownership issues, as possession is 9/10 of the law, right? If Elon Musk starts dropping starships onto the surface of Mars, who's going to stop him, and by what method?
Yeah, enforceability is a big issue, right? Because we've had this this document, the Outer Space Treaty, since 1967, which was put together, like ratified or acceded to by just about every nation that exists, including all of the ones that have space programs. And that really sets forth a lot of how we've thought about like what humans are allowed to do in space and what they should do. It includes things like you can't own another celestial body or a part of it. You can't put weapons of mass destruction in space. You shouldn't contaminate other worlds. There's all of these things that exist in the Outer Space Treaty. But again, having spent this year, for example, reading the work of indigenous scholars, when you're in the nation's capital, you are faced with the fact that every single treaty that the United States has made with like American Indians has been broken. And there's hundreds of them.
Yeah.
Like literally hundreds of them, and some of them are in the same building with you.
Yeah.
And so, that was pointed out by one of the panelists at one of the public events that I had, who's a historian, Margaret Hiddle. And, so I think that, American Indians or indigenous people throughout the world know that treaties are malleable. And that one of the chief things that destroys treaties is often corporate interests, profit interests, whether it's actually corporate or governmental. So, things like the Space Act that was passed in 2015, like that's a piece of legislation that now says that, okay, you can't own a celestial body. So I can't own Mars. I can't technically own real estate on Mars, but now you can own resources on Mars. Well, what's a resource? Well, it turns out a resource is like rocks or minerals, but it's also water
or air.
Yeah, and so then you run it up against like the kind of work that astrobiologists might scientifically want to do on a planet where like Mars is like one of the places that we might have the best shot at figuring out whether there was life that was independent of life here on Earth. So if you go around and you like contaminate the surface, or you make certain parts of it inaccessible, or worse yet, okay, so you can own water, but you can't own it by the Space Act. You can't own life that might be in the water. So does that mean that a company that wants to control water resources can then kill the life that's in the water? That's like the only life that we know of off Earth.
So what I'm getting is that it's complicated. So let's move on.
Yeah, it's complicated.
So let's talk about exoplanets, and let's talk about weird stuff in planets, or weird stuff in the search for planets. So you're using big data to scan the skies for weird things. Can you go into that a little more?
Yeah, so this came out of the work that I did with NASA's Kepler mission, where I, for many years, studied the light curves, the measurements of brightness with time that Kepler takes, not just to look for the little planets that are in there, but to study what the stars themselves are doing, because the stars are shining on those planets and irradiating them and maybe making things more interesting for life, either in a good way or a bad way. So I became very interested in the sort of unusual data that Kepler would take from time to time. The most famous of these is Voyagen star. This is this thing that got written up as like an alien megastructure a couple of years ago. Basically a star that is varying in ways that we don't usually see and don't fully understand. So I became really interested in the role of, for example, citizen scientists who are poring over this data visually and come across things that are unusual and unlike the professional scientists who are sitting there and like have tunnel vision for the one thing that they study. Citizen scientists have this wonderful history of making serendipitous discoveries in projects that have been transformative, whether it's new kinds of galaxies or Voyagen star, whatever it happens to be. So at the same time, I was working on the Large Synoptic Survey Telescope, which is still currently being built down in Chile, and it's going to give us this huge pile of data to work with. And
that's
I
like an understatement.
Yeah.
Petabytes of data dumped onto the internet to
all the time
through.
For everyone to use, right? But the question is like, okay, so what if you have too much data to actually look through? Even like if you had all the citizen scientists in the world looking at it, it would still be kind of slow. So I was really interested in using machine learning to sift through that data. So what is machine learning? It's machine learning actually affects your life every day in a variety of different ways. It's basically a family of computer algorithms. The ways that we most often interact with various kinds of it might be, for example, when you get sent coupons in the mail, that packet of coupons is increasingly, like, companies are interested in tailoring those coupons to you, right? Because if they send you the coupons that you want, you might go into Target or wherever.
But a lot of this work, right? Like computers were in the past super bad at certain kinds of tasks, like recognizing the direction that galaxies were spinning, or spotting, for example, potential Kuiper Belt objects that New Horizons should go to, and then citizen science groups like Zooniverse and what we do with CosmoQuest sort of appear to let humans take on those tasks. But now I know the computers have come back. They've come rushing back with better and better abilities to catch up to what was the last bastion of human science.
Well, but there's this like synergistic relationship, right? Take, for example, Supernova Zoo. So this was where citizen scientists were better than computer algorithms at finding supernovae, or the exploding stars, in these images of galaxies. And the citizen scientists created essentially a data set that could be used to train the algorithm that actually improved the algorithm and made it better than the citizen scientists. But the thing about that is like that, okay, so maybe people don't have to look at pictures of supernovae anymore, but that's okay, right? Because there's always a more complicated problem.
Right.
And so the cool thing, I think, is actually being able to give citizen scientists more nuanced and interesting projects to work on that really like can't be done by computers. So I don't think that it's necessarily like this versus this. I think they definitely work together.
Right. So it sort of changes the class of the kinds of questions that scientists can get answered thanks to the training that humans are continuously giving to the computers. That the computers are, tackle the easy stuff, and the humans train them on the harder stuff, and then that becomes, so it's a back and forth. But like with the LSST, I mean, even with Kepler, I mean, there were all of these interesting anomalies. Everyone is very familiar with Voyagen star. Are there other anomalies that was found in the Kepler data that you're interested in, that maybe people aren't familiar with?
I think the one that I was really most impressed by that happened before Boyajian star was the heartbeat stars. So the first of these that was found in Kepler, yeah, I remember when we all saw it and we were like, what is that? So it was this little thing kind of like up and down, and then these huge like upward spikes, like brightenings in the star. And like we're used to seeing lots of things that make stars fainter, but not things that make like stars brighter. And it turned out that, you know, it's not alien megastructures or anything like that. It happens to be these two stars that are both oscillating. So they're both pulsating. And so they naturally get brighter and fainter. But then they're also in this very elliptical orbit. So when they pass by each other, they kind of ring each other's bell a little bit. They like excite those pulsations so they get brighter. And so every time they go whoop in their orbit, the brightening spikes come. And there were others of those aside from the one that was first discovered in the Kepler data set. It's just that nobody really knew to look for them.
And these are the kinds of things that no astronomer ever was imagining would be the kind of thing that you would notice. It's only when you see this weird signature, you then have to go, okay, what's going on here? It's those happy, unexpected discoveries that you get a chance to make.
Yeah. So the thing that we're doing is we're trying to use, so, you know, we talked about like Supernova Zoo and like the labeling and training of algorithms. The thing that my graduate student, Janelle Giles, and I are working on is to take what are called unsupervised learning. So there's no training of the algorithm or anything like that. And to have those algorithms sort out the things that are most dissimilar from the rest of the data set. So this doesn't necessarily give you, you know, like immediately, like you might find Boyajian star. It gives you basically anything that's rare in your data set or things that are truly unusual. So that means that, you know, you might have some garbage in there, like data artifacts, bad data, you know, just things that look weird for whatever reason that isn't like exciting new astrophysics. You might have things that are just rare in your data set. So, you know, like heartbeat stars show up in there. And then you might have things that are really unusual. And the idea is to take a big pile of data and create a smaller list of things that might be interesting new phenomena. And then, you know, that would be, I think, where citizen science comes into it, is that you still have all this detective work yet to do. And it's the kind of detective work that like the citizen scientists who work on Planet Hunters already do all the time. You know, people pick out interesting light curves. There's like whole discussion forums on everything. It's really impressive. And so, you know, why not do that intentionally on a larger scale?
Yeah. And of course, the larger scale will be when the data from the LSST starts getting dropped onto the internet. So are you sort of preparing and training your algorithms and getting ready for that day when the data jumps up? But there's stuff like Gaia. I mean, there's a lot of amazing missions that are, you know, survey missions that are just dumping all of this data onto the internet. Are you finding that your algorithms are getting ahead of the data, or is the data getting ahead of your algorithms?
We've just been developing the method on the Kepler data so far, but it's definitely applicable to stuff like TESS, the Transiting Exoplanet Survey satellite data, and Gaia. So, you know, I think we're excited. Nobody's ahead of anybody yet. We're just excited to give it a try on some different data sets.
Right, but I just sort of imagine this time when there's, like I said, you know, LSST, when there's petabytes of data there, and your algorithms are just choking on the amount of stuff to scan through to search for these little anomalies. You're going to be needing more computers, more help, more citizen scientists.
Yeah, we're definitely going to need more than just like our personal workstation.
Yeah, exactly. Well, so if people want to get involved in the, you know, want to help train a computer and get involved in some of the citizen science that you're doing, where should people go?
Well, so the citizen science side of it is not up yet because the method is super new. So if they want to get involved in citizen science, they should definitely check out some of the existing citizen science projects that are out there. But maybe keep an ear open because it'll be a little while yet. But
okay,
that's something we definitely want to do.
As soon as you are ready, let me know, and we'll try and help get the word out. You know, to help get the science ahead of the data. Well, if people want to find out more just about what you're working on, where can they follow you?
You can follow me on Twitter. I'm Shakalulu, SHAKA_LULU. And that's kind of the best place for the news. My website will be back up sometime soon. I'm redesigning it.
Well,
but
awesome. Yeah. Well, it was great to talk to you. Great to catch up. Thank you for all the work that you do. I really appreciate all the work that you did with Kepler, and of course in helping us sort out the ethical conundrums of living in space. I can't wait for us to actually find out when reality hits the theory that you've been working on. Thanks for joining us on the Weekly Space Hangout, and don't be a stranger. Come on back.
Thanks for having me.
All right, see you later.